Okay. Hi, this is Paul Rodriguez. We're here today for a quick introduction to machine learning on Comet. This is our webinar series. And we go from what, 11 to 12:30, I believe. Okay. So I'm gonna go ahead and start. If there's any problems hearing or listening to me, go ahead and ask questions. We have a couple people here monitoring the list of participants. Again, my name is Paul Rodriguez. I work here at SDSC. I'm part of the Exceed Extended Support and Novel Innovative Project support, team. I'm going to do a presentation today that, again, it's kind of a quick thing. I'm trying to hit many different areas, and it's in some parts I'm going to go slow. In fact, I'm going to start out slow and go fast in the end. And I'm going to go, I'm assuming this is a wide audience, so I'm going to start out with sort of broad strokes overviews on machine learning and some concepts. And then I'm going to go into deep things later, looking at R and deep learning with a particular emphasis on how I see things running on Comet. There's going to be a lot in the middle that I'm not going to cover. So it's going to be easy and hard and not much in the middle. But hopefully it's a little bit of something for a lot of people, or hopefully everybody. And I want to just give a quick mention that this is part, what I'm presenting is for the most part based on a workshop that we do. And this is something we do over 2 days. And I do this with my colleague, Mai Nguyen. Here at SDSC, and we do this typically in our summer workshop program. So I'm condensing 2 days into an hour and a half. Think of it that way, which is a little bit ambitious. And so if I go fast at times, you can always ask me questions later or as we go along. Okay. Uh-oh. All right, so quick overview. Again, we're going to start out with just some basic ideas. Talk about modeling, machine learning, the main activities of modeling, and talk more about R and how R runs on HPC, deep learning, and digit recognition. And again, the title here is machine learning, but at times it's more about general data analysis and strategies. A lot of terms out there. This is just some word cloud I pulled out from the cloud somewhere. And you can see there's, we've been hearing lately, it seems like there's been a lot of buzz about different things. And so really, what are the key ideas? Well, we talk about AI. It's been getting a lot of press. And typically people mean something, human-like, face detection, person tracking. This term data mining used to be a big buzzword, a little bit. It's still a big buzzword, but it used to be even bigger a few years ago. And essentially, to me, data mining was about, gathering data, looking for patterns and associations, like who buys what products. And it was really, I think, big because of all the internet data that became available in the last 10 years. Big data is a term that also used to be around a lot. And of course, with the internet, we now have examples of big data, like big social networks, lots of internet activity, big science. Uh-oh. Am I too low? Maybe my volume was too low? I don't have a headphone with a microphone. Okay. All right, so if I talk louder, does this help? We don't know why more people can hear me than not. Okay, so it sounds like there's still some people who can't hear me very well, but a lot of people can. Okay, we're gonna get a headset, and I'm gonna talk loud for a little while, but that's okay. We'll try to keep going. Again, I'm just looking over just some basic terms that we hear. Predictive analytics is another one of these terms that people we hear a lot of and sort of gets thrown around. It really just means predicting unobserved data. You know, the recommending movies, when you go onto Netflix, they recommend movies for you. This is a kind of predictive analytics. And it's usually meant to be a contrast to classical inferencing, where classical inferencing is about your in-sample statistics, and predictive analytics is really about your out-of-sample statistics. Okay, but really machine learning, I think, is the term that, to me, we're going to try to understand better. In a sense, what we mean by machine learning is improving system performance with data, such as statistical learning, also, you know, having models that where you fit parameters so you can learn some kind of function. And when we talk about machine learning, we are typically talking about a process where we gather, prepare data, we explore the data, we build a model, and we evaluate, and then you iterate. If you're coming from the data, from a sciences, you know, this is the kind of thing you might do in lots of science anyway. So sometimes we talk about data science, but to me, data science is really just, you know, doing typical machine learning stuff. I think the term data science sometimes also gets thrown around a lot as a new, great, amazing thing. And again, I think a lot of that is because now with the internet, we have all kinds of new sources of data. Okay, what do we mean by gather and prepare data? You clean your variables, maybe you transform variables, you organize variables, and maybe you do variable selection or dimension reduction. We're going to talk a little bit about the variable selection. Cleaning variables, transforming variables, these are things that essentially come down to knowing your variables. Okay, and one way to know your variables is to do summary statistics. We check missing values. We do kinds of visualizations. In the next few slides, I'm going to show you some, I'm not going to talk about these in detail, but here's some examples of how you might use R to get some summary statistics, taking means, variances, you know, looking at quantiles. R is very good for that. You know, looking at histograms, correlation plots. And those are the kinds of things that, you know, you spend a lot of time with, but they're really necessary to do good machine learning. When we talk about machine learning models, we can differentiate between classification regression models, which are supervised learning because you have some kind of target or outcome. If you don't have a target of outcome, then you have some unsupervised learning. And for that, we do procedures like clustering or matrix factorization. And whether you, even if you have supervised a learning situation, you might do clustering also, or you might do matrix factorization. We're going to talk a little bit about that. So there's all kinds of processes that, you know, you kind of build and combine. A lot of people don't really talk about Bayesian learning in the context of machine learning. Really, Bayesian learning to me is something that can come up in almost any situation. It's almost, I like to list it because I think it's kind of important and useful. Hang on a second, I'm going to try this microphone. Okay, that's it? All right. Okay, I hope people can hear me a little bit better. I have a headset on. So I'm going to just mention, the other thing about Bayesian learning, you know, the important thing is that you're learning probability distribution. So not just making a prediction, but learning something about the entire probability of, let's say, possible outcomes. It comes up a lot in HPC settings because HPC has a particular advantage for doing certain kind of procedures with Bayesian learning. And we'll mention a little bit about that too. All right, so let's just start with a simple data example just to sort of get ourselves going, get our intuitions pumped up. So imagine I have some data. The x-axis is home runs. The y-axis is winning, losing percent. This is teams in the American national. This is the, let's see, I can't remember. It's baseball teams from 2012. I think it's from both American and National League. And as you see, in general, as you hit more home runs, you tend to win more games, but not completely. And we can fit a line to it, okay? And this is just regression. We have a couple parameters. One of the parameters is called the slope. The other parameter is called the intercept. We fit a line, and we have a certain amount of error and a certain measurement of how good our line fits. And so that's something we could use that that's a model of our data. We could use that to make predictions of the percent of one and winning and losing. If we want to just do classification, we could take our data, for this particular example, and we can say, let's say that anybody who has a winning loss percentage above 50% is going to be classified as a 1. And any team with lower than 50% is classified as a 0. And so we can end up with this kind of data. So sometimes you have outcomes that are just categorical, and it might look something like this. So on our x-axis, we have home runs. Our y-axis is either 0 or 1, winners and losers. And if we wanted to make a prediction, we could easily just put a line somewhere and just say, well, look, if you hit more than 150 home runs, let's say you're probably a winner. Less than 150, you're probably a loser. And it's not a perfect model. There's some errors, but it's a reasonable way to go. If we have, now let's make this a little bit more interesting. Let's say we have two variables. The x-axis is number of home runs. Y-axis is ERA, earned run average. And we have two classes, the winners and the losers. And we have the winning teams are colored in black. The losing teams are colored in red. And so we can also, again, fit a line. And here, I've drawn the line. This is actually a line that would exist in, 3D, right? Because you have our x. It would be in the axis coming out from the screen. But if we project it down to our two-dimensional plot, we can draw this as a line that separates our two classes. Okay, and we sometimes call this, again, we call this like a threshold line. Okay, so if we're clear on, I'm gonna make a big jump now. So that's just a linear model, and that's just saying, look, we can fit lines, and we can, all the things that we do when we fit lines are the same things we do when we fit more complicated models, whether it be neural networks, support vector machines, whatever. The main thing to think about is that whenever we do models, we have all these choices. We have to decide, are we using linear functions or nonlinear functions? What are we going to optimize? In the linear model, we're usually optimizing some kind of prediction error or minimizing our error. And if we're doing classification, we're trying to minimize the number of errors, maybe. If we're doing something probabilistic, we were trying to maybe maximize probabilities. And then you have to think about, well, what is the algorithm? How do we actually fit these parameters? There's a lot of, with a linear model, there are certain analytical things you can do, or you can take derivatives. And that same thing goes for more complicated models. So we have to have some way to search the space of solutions, some way to impose constraints, and hopefully some way to impose assumptions in our model. And here's another big step. So if you can understand and be clear on what a linear model does, then all the other models you see out there are really just further complications, either in the algorithm, either in the kind of error, or either in the kind of function. So if you start with a linear regression and you say, well, instead of using a linear model, let's make it a logistic function, then you have logistic regression. If you say, well, let's use probabilities and let's assume independence, you can get to a naive Bayes model. So all these models have some kind of variations on how they're built, and they're usually built around some idea about what makes sense for a particular situation, and then they sort of fill up the space of all models. So I'm not going to go through this, of course, in detail, but I just want to show you that the basic idea of what we're doing with modeling. And when we do this in practice, we have to keep in mind that model complexity sometimes can be lead to overfitting. So if you have more parameters, that could be good because you have more complicated functions that you can have. but it's more complicated. It's more potential to overfit. And so you have to be careful about overfitting, and you have to use training. You have to use your data wisely. You have to have some kind of way to cross-validate your model, and presumably you're going to use some kind of separation into a training and test set. And sometimes we even use a training test set and then different cross-validation validation set. So in general, though, I always tell people start simple with models, consider the trade-offs as you get more and more complicated. I typically find that a lot of models are good in some domains, or they've been used in some domains. Sometimes you'll find that, in genomics, in certain situations, people like the logistic regression or probit regression. But in other domains, maybe everybody's using support vector machines. So sometimes, sometimes there's like I don't want to say a convention, but, some precedence. What I find is that, lately, especially these last few years, R, Python, and MATLAB, these are scripting languages, and they're starting to look more and more alike. They're starting to have a lot of the same standard models, and they're starting to develop libraries where there's a train function, a predict function, a test function. They take the same kind of arguments. And so, depending on what your situation is, you could be successful with any one of those languages. There's also some good GUI tools. Weka is a tool that I use from time to time just because it's, a nice GUI interface. KNIME is a tool that some people really like as well. It has some nice features. And that's all I'm going to say about those right now. Okay. Any questions so far? Go ahead and you can type them in, and maybe I'll hopefully be able to address it. I want to mention something about unsupervised learning, and the idea of clustering looks something like this. In this picture, I have two variables, x1, x2, and on the right side of the screen, I'm showing some R commands just to show how I generated the data, just to sort of have there as a record. If I had this data though, and I asked you how would you cluster it, it would be, it'd be pretty easy. You could say, oh, like there's two different groups of data. And remember, with clustering, what we're looking for is there some natural grouping? Is there some grouping that makes sense? If there is a natural grouping that seems reasonable, then that means that there's something in the data, there's some structure in the data, there's some way we could represent the data that has some interpretation, even though we don't have an outcome or a label for individual rows. K-means is a standard algorithm. I'm not going to say too much about the details. It's been around a long time. It still works in a lot of situations. There's a lot more specialized clustering algorithms for different situations. But K-means seems to be, it's a good place to start. And it's actually, even in the last few years, there's been some improvements in how robust it is. And it's just something I want to mention about clustering. Imagine I have these different data sets. I said, can we cluster this? Is it, which of these are easy to hard to cluster? So if you look at the upper right, graph A, again, two variables, and that's pretty easy to cluster. B is a little bit harder, but you might think it's just one cluster. And so maybe it's easy to cluster that way. C, a little bit harder, but you might think maybe two. And here's a potential way to cluster those two. D, now D is actually pretty easy. It looks like there's 4 clusters. Okay, now imagine I said that, by the way, this data actually consists of 2 different classes. So the upper left, A, there's some red dots and blue dots. They belong to 2 different classes. And then I said, how could we classify this? Can you draw a line that separates these points? Again, if we're thinking about a line, that means we're thinking that there's some linear function. The linear function is going to give us some threshold to tell us when when our x values are part of class 1 or class 2. Okay, so for the upper left, that's pretty easy. You can draw a line right between those. For the lower left, figure B, it's still easy, but you can see that now we're starting to have a case where there's potential errors. Some of the points, if you drew that line with a little different angle, maybe it's going to be a better separation, maybe it's worse. It's a little bit harder to say. In the upper right, that's very hard to separate. You probably need something that's nonlinear if you're going to have one line. The lower right, okay, that's even harder to separate, something highly nonlinear.
So there's a couple of questions.
We have a couple of questions.
You always have to visualize the data to decide which model to use.
Okay, we're going to talk about visualization. We are going to talk about that. That's a good question, and we'll get to that.
The other one is, how do you define machine learning in a line?
Okay, how do we define machine learning in a line? I think, I guess again, if you remember, we're thinking about machine learning as statistical learning, which is a more generic term. Then, fitting a line using some statistical procedure is kind of an example of machine learning. Nowadays, people, when they talk about machine learning, people tend to mean some advanced model. And that's, maybe that's just the way people talk about it. But really, there's no, in practice, really, there's no, let's say, hard separation between when you're doing machine learning and when you're just fitting a regression line. Fitting a regression line can sometimes be a useful thing to do. I'm not sure if that answers the question. I hope it does, but I'm going to go ahead and go on. And if you have more questions, yeah, keep typing away. But the summary of what I want to get to here is that if you do clustering and you're doing classification or one or the other, there's no easy relationship between clustering and classification. Sometimes things can be easy to cluster and hard to classify, or vice versa. But if you have a situation where things do cluster well, and let's say it's easy to classify, then that sort of gives you an idea that, okay, sometimes things that cluster well will classify well. Maybe we can visualize. We'll talk a little bit more about that. Okay. All right. The other kind of process you might do if you have unsupervised data is called matrix factorization. If I have a numeric matrix, you can ask the question, well, can we reduce the number of columns? And if you have variables, sometimes I use the word variables, sometimes I use the word features. Depending on the situation, they're really interchangeable. If you have variables or features that are constant, you can reduce your matrix. If you have variables that only contribute noise, you could reduce your matrix. Or conversely, you could say, you know what, I only want to keep features that contribute to variance, the variations of the data. So let's look at an example. I'm going to present this graphically. Let's say we have two dimensions again. We have height, and in the y-axis, we have weight. In the x-axis, and this is athletes' data from one of the last Olympics. I think it was 2012, actually. And I asked you, okay, here's a bunch of data. I've mean censored the data so that the average is 0. And I say, find a line that aligns with the data. Okay. So what I mean is something like this. Here's a line that lines up with where the data seems to, sort of the trend of the data. Okay. Now that line also lines up with where most of the variance is. And in fact, we can make an equation for a line where height is 0.8 times W. And we can say, look, if we take the 2.00 and the other coordinate point of 1.8, 1, 0.8, those are points of the line. We can represent points away from 0, 0 as a vector. Okay, so here's a column vector of 1 and 0.8. And then we can find another line that's orthogonal to the first line. Because you have two lines that are orthogonal, it also covers the space of all points there. And we could take both those vectors and put them in a matrix. as column vectors. And then we can then rotate the whole thing and say, look, instead of the original H and W, now let's work with these new lines. Okay, so these are new axes. They're really combinations of the old features. And if we wanted to, we could say, well, let's throw away the second line and let's just keep the first line, which had most of the variance. Okay, so that's an example of dimension reduction. And these are basically, the procedure I just went through is basically a kind of factorization. Sometimes it's called matrix factorization, and sometimes it's more, there are general procedures called singular value decomposition and principal component analysis that are well known, and they work to basically give us factors. So you can use these, and I'll show you an example in I think a little while. We can use these to do dimension reduction and help us with visualization.
Quick question. Is there any limit in the number of dimensionality in K-means cluster?
So the question is, is there a limit or some kind of something to watch out for when we use K-means with high dimensions? And in principle, there is no limit. Your issue with K-means has more to do with whether or not variables are on the same scale. So if you have some variables that are very large, you may have to transform that variable so that it doesn't dominate your, let's say, your measure of distance, or you use some kind of different metric. So K-means, I have used K-means with large vectors and found useful results I'm sorry, with large number of dimensions, but I do have to be you do have to be careful with, let's say, variables that have very low values or variables that have super high values. Okay. I'm gonna switch gears now and talk a little bit about R, and we'll go through an example with on the clustering in SVD. Okay. So when we lose R on Comet, typically what I do is I'll get a compute node, and in order to start R, we load the module, and you execute R, and it gives you an interactive session. And when you exit R, you do a quit, you exit the compute node. So that's running R. That's a basic sort of interaction way to get an interactive session with R. What I'm going to do is show you real quick a quick example using R. And I'm going to use a Jupyter Notebook. And the Jupyter Notebook is going to give an interactive session so that we can actually get plots and have it up on our screen and view it through a browser. I'm not going to go into details of this, but I'm going to switch screens real quick into, I've already executed these commands, and so I have a browser window up and running. Hang on a second. Let's see if I can find my browser window. Okay. All right, can you guys see the screen? Yep, I need to, hang on a second. I need to change my sharing. New share, is that right? Do I hit new share? If I want to switch screens? There we go.
You want to share your entire desktop?
Oh, is that right?
Or specifically, but it's easier to just share your entire
Yeah,
desktop.
do you see it now?
Yes.
Okay. Okay, so sorry about that. Okay, so I'm on a browser window. I followed those instructions. I opened up my, I'm actually looking at the files that are on the HPC system, and I have a quick introduction to R right on HPC. This is a Jupyter Notebook. If you haven't used a Jupyter Notebook, basically I have a bunch of R commands intermixed with a bunch of text. The Jupyter Notebook knows that it's only going to execute R, only execute certain lines of code. It knows which is code and which is text. I'm going to clear all the output. So I'm going to, okay. And in my notebook, I have some descriptions, and I have R code and some other descriptions. I'm not going to go through everything here. But some of these are just basic R commands, and some of these are more to the point of this tutorial. Okay, so the first part here, I'm just reading a table. R is nice because it has certain ways to read, CSV files and typical text files, and it has some parameters to just, read a header. You can tell it whether or not a string should be interpreted as a factor. So R reads everything into what's called a data frame, which is just a heterogeneous data matrix. So it's not just numeric, it can be strings and numeric, and take the strings and interpret these factors. Okay, so I'm just gonna go into cell. Run cell. Okay, so I can just run that cell. There's a bunch of, I'm not gonna go through all these commands. There's certain commands to just quickly view your data frame. R has some commands that are nice to just select off which rows have complete data, change the format of variables. Now what I've done here, let me show you real quick what the data is. So this is data that just has a bunch of weather data from someplace in Australia, Canberra, Australia, and it's got a bunch of columns, and one of the last columns is whether or not it rained tomorrow. So we're gonna be interested in knowing whether it rains tomorrow, see if we can predict that. So it's just a simple prediction problem. I'm extracting that particular variable. I'm cleaning up the data a little bit. I'm going to prepare the date field. So R has some nice way to deal with dates. R has a nice way to do reshape your data. So I'm going to just change around. So if you have repeated measurements, and if those repeated measurements are listed, let's say in separate rows, but maybe you want them in separate columns, you can use these reshape commands to change that around. Okay. All right, so it added a bunch of columns. I'm not going to go into the details here, but they're based on wind speed and the particular wind direction. Now, those used to be different rows, and now they're all in the same column. Excuse me. And in R, we have the option to do singular value decomposition. So I'm going to take the data. I'm going to get all the numeric values out of there. Okay, so now I have a matrix of just, I'm going to turn it into a data matrix. So I take the data frame. I said, just give me which ones are numeric. And now I'm going to actually make it into a matrix. So R understands it as a matrix. It can do computation on the matrix. I'm going to scale it and mean center it. And now I can run SVD. So SVD is just, the command for that is just SVD. It gives me some outputs, which are factors. And I'm not going to go into detail of what all these mean. But we have different, we have a certain number of factors based on the size of the original matrix. Okay, and now I'm going to run, so I'm just going to keep this, leave that there. I'm going to point out that the U and the V are the factors we're interested in. And I'm going to run a k-means cluster analysis. And then I'm going to take the first two factors from the SVD analysis. I'm going to plot k-means onto those factors. Okay. So let me just show you what I did here. I ran k-means. I said, let's use different colors. I used 4 different clusters. I took the data points and I projected them onto the 2 factors from the singular value decomposition, and now I'm plotting. Okay. So remember, the 2 factors from singular value decomposition accounts for the most variance, the 2 most variance. So therefore, you might think, okay, at least in these 2 dimensions, I'll visualize something. Maybe I'll be able to see something. What you find is typically often the case with k-means, k-means will always give you some answer. Are they good answers or not? It's hard to know what the right number of clusters are, but it's sometimes useful to try different values. Here we see that there's 4 different clusters by 4 different colors. they're not well separated. There's a lot of overlap. There's no clear delineation. So we might think, okay, well, so the clustering itself is not very satisfying. Okay, and so let's now try a classification. Okay, so I'm just going to pull out some classification. So what I've done here, as I've said, I've made some classification based on the weather. Remember, we're trying to predict the rain, whether it rained the next day. And so we have two classes, red and blue. I can't remember. I think red is no rain and blue is yes rain. And I've taken all the data points and projected them into two dimensions. Again, the first two singular value decomposition values, factors, I mean. And I plot that in two dimensions. And now we can see that when I plot the classes, it is the case that the blue tend to be a little bit lower on this down here on the two dimensions. And the red covers more on the upper half of the two dimensions. So maybe there is some chance for, a model to learn something. At least in these two dimensions, it seems like there is some separation. Remember, this problem has, I think, 14, 15 dimensions. So I'm only showing you two dimensions, but they have the most variance. So if the model does predict well, that means there's other stuff going on in the other dimensions that we're just not seeing. Okay, so let's do a linear model, summarize it. Just summary of the original y values. And let's look at the predictions. And what I'm showing you here is the confusion matrix. So just this linear model, it actually does pretty well. So it predicted one, which I think was no rain, and it got that correct 259 times. And so those are true predictions, and predicted yes rain 29 times. It did have a lot of failures where it predicted no rain, but it in fact did rain. Okay, but let's now color the predictions. Now we can do some visualization. We can, again, I'm plotting this on two dimensions. And this time I'm showing you the colors by the class that was predicted, not by the actual class. Okay, and so we see that in two dimensions, sometimes for these two factors, we're getting predictions of rain right next to predictions of no rain. So there is some intermixing. So we know that there's a lot going on in the other dimensions. We just can't see it very well. And finally, we could plot the errors as well. So now I have a plot where I have the correct predictions correct predictions for no rain in red, correct predictions for yes rain in blue. The yellow are predictions for rain, or predictions for no rain, but it rained. I think the black are predictions for no rain, predictions are for rain and it didn't rain. So anyway, you go back to the confusion matrix and you would line it up. And you see that, sometimes we're making predictions very close to correct predictions, but they're an error. So the whole point of this is to say, okay, look, we can do some visualizations. They give us little clues. They don't, it's hard to get the full picture in all dimensions. But again, we're just combining the unsupervised technique with the supervised technique. Okay. So this, I ran this in Comet. This is running on a single compute node. This is small data, so it runs pretty fast. When I don't often use a notebook. I typically just use R and batch. And what I'm going to talk about next is using R and scaling R. Okay, so I'm going to minimize this window. Actually, I need to share let me share my desktop. So let's see I'm not quite sure how to share the desktop.
Did you stop sharing and then reshare?
Okay, stop share. Can you give me a second?
toolbar hides. So if, yeah, down there. So if, or move the cursor down to the bottom, all the way. Whereas, oh, you are sharing. Oh yeah, okay. So desktop and then share.
This one?
Yep.
Oh, screen, it says.
Yes.
Oh,
very
screen,
good.
okay. Okay. All right, let me go back to my presentation. This was the tutorial. All right, let me talk about running R. So again, for those of you using R, I often start doing things on my PC. There's a tool called RStudio. RStudio has a nice environment. If you're learning R, it's nice because you can have a window where you edit your commands, you can run your commands, you can see plots, you get help. You know, here's just a typical, if you haven't seen R before, it's really a statistical programming language. Has all these kinds of nice built-in functions. You know, the reason people like R is because it's, you know, has a lot of statistical functions. It's really developed by statisticians. It's on the HPC side, it can be really useful if you're doing big bootstrapping or sampling methods. If you're gathering big, you know, large amounts of data and trying to transform it and prepare it for models. And again, certain statistical procedures that are there in R that you typically don't find in MATLAB or Python, especially some of the routines that seem to be of interest to social scientists, imputation methods, certain kind of regression. When you're scaling R, basically, when we're scaling R, you know, there's different things that you can do. R does take advantage of the math libraries for vector operations. So certain, you know, vector operations can be pretty quick in R, just running on a single node. There are ways to do multi-core and multi-node calculations. Spark R is an option if you have like a lot of distributed data. And what I find though is, you know, sometimes we don't have models that use the parallel backends. So sometimes we have to implement, we can implement multi-node execution just using our Unix commands. And I'm going to show you an example of that later. Okay, so just real quickly, again, if you use an R, a lot of data, this would be true for lots of systems. Certain, if you do have large matrix operations, you know, certain things you can do to solve matrix operations. So for linear models, sometimes you have to break them out and do different matrix operations. Certain kind of models that are using gradient descent, for example, are going to be very slow. So this is, I'm showing wall time on the y-axis and data matrix sizes on the x-axis. So you just have to be careful which methods you're using. If you have really large data and you're trying to get it to run in R. When you're doing modeling, you know, the k-means and the linear models tend to be pretty fast. The SVD factoring can be a little bit slower. Something like support vector machines is even slower. I don't have a picture here of neural networks, but if I ran a neural network and it was even much, much slower. So that just gives you a sense of, you know, if you have more data or large data matrices, sometimes you know, the simple models are going to be faster. Okay, to run R multi-core, there's a package called doParallel. It actually works by just surrounding your R code with a couple of little extra commands. There's a library called doParallel. You register the cores on a Comet, that's 24 cores. And then, you know, you have your regular R code, but you have a for loop. Instead of a regular for loop, you have something called the for each loop, and you tell it to do something in parallel. So your regular code gets split among all the cores on the node. And so this works pretty well. You have to be careful of a couple things. The returned items get combined into a list, or you can specify how to combine the items. But the problem could be is that if you have a big data frame, sometimes that gets copied a lot to all the cores. So anything, you know, on Comet, typical compute node, we have 128 gigabytes. if you have a data frame that's 10 gigabytes, and if each core needs all those 10 gigabytes, you're not going to be able to use all the cores. There is a way to run R across nodes, and that requires a slightly different initialization. So there's a package called do-snow, and in that case, we have to make a cluster. You have to tell it, okay, I'm going to use MPI, which is the message passage interface, to go across different nodes. You have to tell it how big, they call it here the universe, but it's just basically the number of nodes you have. You register this cluster, and now you have the same for each command. Okay. But again, you still have a potential issue in that if you have data that needs to be used at each core, sometimes it gets copied around. And so a multi-node process with R sometimes it doesn't work as well as you'd like. I haven't had a lot of good situations where this was the right thing to do. I have had good luck using this other method to parallelize R. So imagine you do have a big data set, and you can split it up. So if you have a situation where the R is going to work on separate pieces of data, can work on separate pieces of data independently, you can just take your data, split it up ahead of time, and then you have a regular batch script for Comet. You tell it, okay, I'm going to run a Perl script, and that Perl script is basically going to execute R for you. So the Perl script tells you what CPU you're on, and then it tells that to R. So that way R will know which data set it can process. So it's just a little bit of MPI, and it looks something like this. You have executed on each core on different nodes. You have a Perl script, and a Perl script can figure out where it is, which node and which core, and then it'll tell R. And so now R can process different data sets, and all you have to do is combine the data sets at the end. So I'm finding that for a lot of situations that you would want to use R in, like the big bootstrapping, some of the big statistical procedures, it turns out this kind of fits the kinds of R processes you might want to do. So it's more programming, but it's pretty flexible. And I'm not going to go through the details of what the batch scripts look like, or this is the example of the Perl program. Sometimes we just call it like we're packing R sessions onto all our cores. And this turns out to be a good way to, if you have a problem with data management, if you have a lot of separate models, if maybe you have a lot of variation in time that each model needs, which could depend, of course, depend on what data set it's processing. Sometimes with large matrix operations, you can do this with optimal. So I'm doing an example with a big maximum likelihood estimation procedure. Okay. And I'm not going to go through these details, but lately, this is just some examples of big R projects we've had, scaling MCMC, Markov chain Monte Carlo method. I actually had 2 of those examples recently, running on Comet. Like I said before, there's another example of scaling likelihoods. So this was an example with 70 million observations. It just took too long on one compute node, and we had to parallelize it. Okay. Finally, one thing about using R on Comet, if you got install packages, it usually works pretty well. Sometimes on Comet, you have to tell it to look for its dependencies, especially if you have a package that needs to be compiled. Sometimes it doesn't quite compile right on Comet, and I find the best thing to do is talk to the system people. You need to go ahead and get help on that. Often it's just a case of having the right libraries for the C compiler. Okay. Okay, I already mentioned RStudio. I do find there's some other R packages. Now, RSpark, I said it was a method when you have a lot of data, distributed data. If you do want to use something R with something like MPI, I find that the PDB, there's a package called PDB-R that runs a lot better than the R MPI. There is some GPU tools that work with R. I haven't had a big reason to use those, and I think a lot of them are still new. I have had occasion to use some of these other tools in R that help you manage big files, and sometimes those can be useful. Okay. I was going to say something about Spark. Spark, again, is a library that helps you handle the situation where you have a lot of data, it's already distributed, and it basically brings computation to where the data is. And I'm not going to go through, you know what, I'm going to, in the interest of time, I'm just going to kind of skip over those. And I'm going to switch into now, do you have any questions so far? I'm going to switch now into the deep learning part. Okay. So deep learning is another term that is associated with artificial intelligence. In a sense, you know, it's just about learning really complicated transformations of your input. But more practically, when people say deep learning, they mean it's using neural networks with lots of layers. Okay, so that's what we're going to try to look at real quick is what does that mean? What does it, you know, neural network, what does it mean to have lots of layers? Remember the regression line example that I gave before? Okay, and we said, well, we could do classification. And before, I said, well, if you want to do classification, you can just do a threshold and say anything greater than 150 home runs means you're a winner. But we can do a little bit better. We can say, let's fit a nonlinear function to this example. So here's a nonlinear function. It's a logistic equation. And essentially, it's called logistic regression. And I'm not going to go into the details of the equation. But if you have a function like this, so the x-axis is home runs, the y-axis is 0. The data is either 0 or 1, but my function can take a value between 0 and 1. And unlike, let's say, a linear line, the output is squashed to a range of 0 and 1. And so now the output prediction is in fact like a little bit like a probability prediction. So the more home runs you hit, the higher you expect the outcome to be a winner. The less home runs, the lower your probability. And we could take this logistic regression idea and say, well, let's just draw it out as a little network. So here I'm showing you the function where the output value is a function of my input and some bias parameter and some weight parameter. And the bias parameter I'm calling, which used to be just beta 0. The weight parameter previously was just beta 1. Here in my graph, it's a weight. The weight parameter is a weight on the input line. The input line is going into a node where the node is creating a transformation and producing an output value. And we call it an activation function. So just by changing terminology, I can sort of make it look like a graph. And we can also use different units. So it turns out with deep learning, people find that rather than use logistic functions, it's nicer to use this other kind of function, a rectified linear unit, because it's just going to be a faster computation. So it's a nonlinear unit again, but it's just a faster computation. And we can make this whole thing more general. We can say, well, we can have lots of input variables. We can have different combinations of transformations. And we can have even different layers. And so now in this example, we have a hidden layer and an output layer. Okay, but again, when you look at neural networks, they're really just, you know, each little node itself is just performing some simple regression, and it's just we have a bunch of connections, and we talk about connections, we talk about layers, and some architecture. But again, they're all based, you know, individually the equations are very simpler, but now what's complicated is the fact that we're combining all these things. And just to think about how things combine. So here, is a logistic function with a couple different kinds of parameters. Here's a logistic function with a higher weight parameter. Here's another couple examples of logistic function. Here's two logistic functions, and you can imagine if I add them together, if these were two different functions at two different hidden layer nodes, and you add them together, what are you going to get? You're going to get something like this. So by combining all these things, you can get really complicated functions. And that's where the power of the neural network is coming from. Okay. Of course, why stop at one hidden layer? You could have different layers where they're all making big combinations. Again, individually, they're all simple calculations, but when you start combining them all together and having some outputs from some nodes that feed into other nodes, which feed into different nodes, and now we have a whole variety of features and transformations that can happen. These next slides, I show some examples of that. I'm not going to go into detail of this slide. I just want to go ahead and to the next part. If I have neural network, now I said I can have these complicated transformations, but the downside is I have a lot of parameters. Only at the last layer do I really have some output value that is supposed to, where I know what it's supposed to be. Do I have a target? So the error somehow is only known for the last node. And somehow I have to take that error and propagate it back to the hidden layers. Okay. And so that's the whole procedure called backpropagation. I'm not going to say much more about that, but it's basically hard gradient descent problem. But it turns out it's not that the gradient descent is so hard. It's just that it's a lot of different calculations. Okay. Okay, so that means we got to be careful when we're training these things. More layers, you can get more transformations, but there's more parameters. The error becomes smaller, especially as you go further back away from the output value. And you need more data and more computing power. So in a nutshell, that's the main thing that has really improved in neural networks in the past 10 years is that now we have all this internet data. We have all this way to gather data. They've been using these simple human task, Turk tasks, Turk procedures. I don't know if everyone's ever heard of the mechanical Turks. To produce data sets with labels, large data sets. So there's something well-known called ImageNet. Someone's collected millions and millions of images, and they've all been labeled as to whether or not they have, what kind of object is in the image. And with GPU nodes, a lot of these calculations have become much faster, and people have figured out some tricks to help avoid overfitting. So you put all those three things together, and the neural networks have become very successful in the last, especially the last 5 years. Okay, so let's talk a little bit more about those kinds of neural networks, the deep learning networks particularly for object recognition. Okay, imagine I have this situation. I have 3 input variables. They're fully connected to an input node. Let's assume there's no bias for now, and that X values are all between 0 and 1. And I said, okay, if I have weight values that are 1, 0, 0 for 3 input values, and I ask you, what is the transformation that this weight times input is going to be? Well, really all it's doing is it's taking my X1 value, but it's ignoring the X2 and 3 values. So if it was if I were going to do also a logistic transformation, it would just be squashing that X1 value. Now let's say I have this situation. I have 3 weights for 3 nodes each. The first node, it's taking the X1 value. The second node is only going to process the X2 value, and the third node is processing the X3 value. And so what's this transformation? This is really like an identity matrix. Okay, so this is just basically taking one three-dimensional input space and copying it to another three-dimensional input space. In this case, it's just going to be the identity. And it really depends on the entire transformation function, but at least for the W times X, for the weights times the input, it's really just transferring it to another space. Now imagine I did this. I had my first weights were 1, 0.8, 0. The second one was negative 0.81, 0. The third one was just 0, 0, 0. Now this transformation looks a little bit like when we were doing the athlete's height and weight transformation. Remember that? That was the finding the vectors that account for the most variance. So for that kind of data, this is just projecting, or rather rotating the data onto those two matrices. I'm sorry, projecting the data on those other two dimensions. Okay. Now imagine you have this. I have weights that are negative 1, 1, negative 1 into the first input node. And I ask you, well, what values of X is going to maximize the weight times X? Okay. And let's assume that the X values is also just plus and minus 1. Okay. So if the X is the same as W, then that's going to give me a maximum value of 3 when you take X times W, or W times X, I should say. So informally, in this kind of example, if you have if you have sort of a spike for your second input node, and your first input node and your third input node, I'm sorry, I should say your second input line, and your first input and your third inputs are negative, it's kind of like a spike. And if those weights are also set up with similar values, it's going to give me kind of a spike detector. Okay. Now imagine you do this. Let's say I take those weight values, and now I'm going to copy those weight values for all the other nodes. So now all the nodes are just looking for a spike in the set of 3 inputs that are feeding into it. And notice that for the first node, I have inputs 1, 2, 3. For the second node, I have inputs 2, 3, 4. The third node is going to be inputs 4, 5, 6, and so on. Okay. So in some sense, this is looking for a spike at every node. And I'm copying the weights, which is the same thing as just sliding the weights along the input. And when you're sliding weights along an input like that and multiplying it by the input, that's essentially a convolution operator. So when you hear deep learning convolution nets, that's essentially why it's called convolution nets. You're taking some weights, you're thinking of it as a filter. In this case, I'm filtering for spikes, and I'm going to take weights and just slide it across an input. Okay. And if we take the output of all the nodes and just take the maximum, now I'm looking for a spike anywhere. So I'm looking for the maximum spike. I'm not necessarily looking for a spike everywhere. I'm just saying, okay, there was at least a spike somewhere. So those two things in combination have become the basis for convolution networks. And let's see how it applies to a two-dimensional image. So here I have a simple image. The black squares, let's say the black squares are -1, the white squares are +1, and I have a diagonal line going from the lower left to the upper right. What would a weight matrix look like that activates the most for this kind of line? Okay, it would look something like this. I would have negative values off the diagonal, positive values on the diagonal, and so when I weight that weight matrix multiplied element-wise by this little image, by this input matrix, is going to have maximum values. Okay, so now let's take the same idea to a complete image. So here I have a picture of a car. I'm going to have some filter. It's going to be applied to some region in the image. So there's a little patch I'm just going to take my filter, apply it to that patch, and I'm going to slide it across the top row, the second row, and so forth and so on. And so this is actually the basis of a convolution neural network. It's for the most part, this is a lot of the parameters that you have to decide, you have to choose when you're making a convolution network. You have a filter, you have a filter, and you have to choose how big is the filter. It turns out that it's useful to have small filters when you're doing object recognition with a lot of different kinds of objects. It's very useful to have a small filter of, let's say, 3 by 3, and that can actually be better than, a little bit more efficient than having, let's say, one filter of 5 by 5. So one of the reasons we'll see that these networks have been increasing in layer, but at each layer it's a small filter. You have to choose how you slide it. How are you going to take this filter and slide it across? Are you going to skip over pixels, or are you going to just maybe skip over one pixel at a time? So the less you skip over, you capture more detail, but it's less efficient. Also the number of filters. So in a convolution network, you're going to have, remember, the same filter is applied to the whole image. So if you have to choose how many different filters you're going to have. Remember, each filter is probably going to be looking for one kind of thing. Maybe one kind of, like I said before, one kind of line in maybe some direction. So when we do these convolution networks and we have filters, we can sort of think of filters as giving us a kind of feature. It could be a line feature, it could be a color feature, it could be a combination of lines and colors. We don't really know. The power of the convolution network is that we don't actually have to build the feature ourselves, we just have to build the architecture and give it enough data. Okay, so what's people have discovered is that with, now that we have lots of data, we have these access to GPUs, we can build really large networks. And this is an example of something called the ALEX network, which was applied to object recognition problem. It performed super well, like I think it's now 6-7 years ago. I don't remember the exact, I forget the date it came out, but they beat the previous, it was an object recognition competition, and then they beat the previous winner by something like a large, I don't know, 10% or something like that. A pretty good amount of performance. And so people realize that by building these large convolution networks, you can get, with a lot of data, and a lot of training, and some heuristics to avoid overfitting, you can get really good performance. So let's zoom in a little bit more. What you have is, in the beginning, on the far left, you have the image. The image is, in this case, 224 by 224. It has 3 channels for red, green, blue. And the next layer, this middle layer here, each convolution layer is using the rectified linear unit. It's followed by this max pooling idea. In this example, there was 96 channels in that second layer. I don't remember how much it was sliding, how big okay, so there you see in this example, the first layer has a filter of 11 by 11. And I don't remember how much sliding was going on. And in let's see, the third layer here, there's now 256 channels. It had a 5 by 5 filter. So different combinations of filter, different combinations of channels. It's hard to know, when people build these things, they try different variations, but they're basically all, there's a lot of, they're not, let's see, it's not obvious what's the best number, but they're using large numbers. Okay, and then the other important part of these networks is that the last few layers are just like they're not a convolution network. They're not using filters. They're using just a standard neural network. In this case, it's fully connected network, fully connected network layers. So they no longer have just like a little 11 by 11 window. It's just basically everything, every node is connected to the next, to every node in the next layer. All right. So when you run something like this and you look at the filters, you get this kind of these kinds of pictures. So you see a lot of filters here that are looking for edges in certain directions. They're looking for maybe combinations of colors. It's hard to say exactly what these filters are doing, but prior to convolution networks, people would just say, let's just build a bunch of edge detectors and let's see, how well we can classify images. Here you have a bunch of filters that, again, they're just, you couldn't necessarily have guessed or predicted what kind of filters exactly the network is going to learn. When you give it an input, so here's another example where the picture of the car, this is not the filter, this is showing you the convolution output at each layer. And as you go up, further up away from the input, you get more and more abstract pictures. It's hard to see exactly what's happening. But if you look at the very last layer, it's a smaller map. It's a little bit, the pixels here are larger. It's not really obvious if they're identifying certain car parts or certain combinations of car parts or certain combination of features. In this case, the output is going to predict the car as well as truck, airplane, and ship to a smaller degree. Okay, so that's, in a nutshell, that's what deep learning is and what a convolution network is. Some of the important highlights here: hidden layers are doing transformations into new features. These features are highly nonlinear. We can think of them as a space of, a new space for the input data. They can be different kinds of filters. And in the end, there's a lot of parameters, a lot of weight parameters, a lot of ways to, find these parameters, and a lot of options for building these convolution networks. So there's still a lot of activity going on in how to build the best networks. I'll talk a little bit more about that. The other important idea is that we're doing feature coding. When we're doing things like support vector machines on, let's say, edge detector a pre-identified edge detector, that's kind of like we're doing our own feature coding. But the convolution network is doing feature discovery. So that's a term that sometimes people use. But if you have a small data set and you have, let's say, features that are pretty obvious, support vector machines, maybe that might be the better way to go. So building features, can be hard. So building features, can be hard. But if you have a lot of data, if you have a large classification problem, feature discovery can be the better way to go. Okay, so let me switch to the tutorial. I have like 10 minutes. Oh, I have a question.
We select a type of filter, like a low pass filter ourselves.
So the question is, can you select your own high pass filter to make computation cheaper, more efficient? And here's what I would say. If you have a problem where the filter is useful, then you should probably do it that way. And if you don't have that much data, especially, you should probably use that with combinations with something like a support vector machine. If you have a problem where you're not sure it's useful, then you could maybe use that in combination with a neural network, or you could use that, or you could use a convolution network by itself and then maybe use that as a comparison. I don't know if that helps, but it all depends on how strongly you feel about how good that filter is. If you have enough data, you might as well just let a convolution network, produce its own filters. Okay, so let me switch screens to, I'm gonna go back to my browser and, okay. So I have another Jupyter notebook here that is going to run deep network using Keras. First thing I'm going to do is I'm going to clear out all my output. Okay. So with deep learning, if you're going to do a convolution network, you're probably going to be using Python. That seems to be, there's a lot of tools. I'll talk a little bit about other tools. This is an example using Keras. Keras is built on top of a library called TensorFlow. TensorFlow has all the functions for doing fast calculations. Keras is just kind of a higher level language that helps us build the networks. This first part, I'm just going to load the Keras modules. If you're familiar with Python, you know, it's kind of like a standard Python set of modules. There's NumPy, there's going to be some plot libraries. Okay. I have some training data, and I'm going to show you what they look like, but these are basically a digit problem. So this is two-dimensional black and white digits, handwritten digits, and I'm just loading them to my session. I'm going to reshape it so that these models expect a certain kind of input, which is, you know, three-dimensional images. So it's not really one data matrix, but it's basically a four-dimensional column. Okay, so I have five. So in the end, I have 5,000 examples. There's really only one dimension of color, and each image is 28 by 28. I think I have, okay, I don't have an example. Later, I think I have an example of the image. We set up a model. Okay, so this is a Keras command. It says set up a sequential model. A sequential model just means I have one layer feed the next layer, feed the next layer. There's other options where you could have an input layer feed two different, you know, paths through a bunch of convolution network layers. Here I'm setting up 16 filters, and I define a convolution layer as having a certain number of filters, a certain size, a certain stride. I'm telling it that, you know, the first dimension of the input is the channels. It's using a rectilinear unit, and there's the input shape. Okay. And Keras, as I said, Keras is built on top of TensorFlow. TensorFlow just keeps tracks of all the, you know, the vectors basically that we're talking about, vectors and matrices as tensors. Okay, so I've created one convolution layer. I'm going to add some more. I'm adding a max pooling layer. So this is a relatively small network. I'm running this on Comet on just a regular node because it's a small network. It doesn't need a GPU node. I added this max pooling layer. I'm going to add some dense layers for classification. There's one of these tricks that people have discovered is useful, something called dropout, where it just basically adds a little bit of noise as the network is running. Every so often, it's going to drop its value to, you know, to 0, and that helps avoid overfitting. But there's other ways to do that. That's just one way that people use. Okay, so I've basically defined a bunch of layers. I told it what the filter, how many filters, how many, you know, how big the filters are, and now it's going to put this all together. And this is a Keras command that's going to compile this into actual network, and it's going to say, okay, it's going to use stochastic gradient descent, and it's going to use a certain function for classification errors called categorical cross entropy. Okay, so it defined how it's going to fit, and now I actually run the fit algorithm, and it's fitting the model. Okay, so it ran And as it ran, my accuracy increased. It's just an epic here just means it's running through the training set. Let's see, 10 times it ran through the entire training set. Okay, and we can, there's some other commands to help you, just run tests. Okay, just to remind you, the output when you run a test is basically some kind of classification value. So here I'm just showing a couple of output vectors. Remember, there's 10 digits, so there's 10 outputs. Okay, so here I'm going to look at a sample image from the training set. Okay, so this is what the training set looked like. So that's actually number 5. And now a couple things we can do. So now I've run a model, I've trained it, and now we can go and look at the actual filters. Okay, so there's some commands to help me get the weights from the model. And I'm just going to do some manipulation of those weights, and I'm going to plot them into a mosaic. So remember, we had 16 filters. Okay. And each one filter here was 3 by 3. So what I'm showing you is for the 16 filters, this is what the filter looked like for the first of those 16. And if you look at these filters, it's not really obvious what kind of feature they're trying to detect. It's tempting to look at some of these filters and say, oh, maybe this is detecting a combination of, let's see, what's a good filter here? Yeah, none of these, it's very hard to know which ones. I mean, this is like a combination of some dark area over a bright area. But that's about all you can say. Now we can also visualize, well, what does the activity look like? Okay, so what I'm doing here is I'm just executing some Keras functions. I'm getting the output activation, and I'm going to show that as a mosaic. Okay. So remember, there were 16 filters in that first layer. When I gave it an input image of 5, this is what those 16 filters produce as output. Okay, again, because it's an input, it's a 2D input, it's a 2D output. The output is a little bit compressed because I'm doing a sliding filter, and I'm also taking a maximization over little windows. So it's a little bit smaller than the original image. And in some cases, it looks like it's not really transforming the original image very much. In other cases, like this first row, third column, it looks like it's just picking up on a few parts of that image. I think maybe in this last row, first column, it's maybe highlighting a certain section of that image. It's hard to know, but that's the kind of thing that goes on. If we do, I'm going to scroll up real quick. I think I have just enough time. Back to, first of all, I'm going to clear out all my output. And I'm going to go back to where I chose, let's see, where did I choose the filters? Okay, so instead of a 3 by 3 filter, I'm going to make this 9 by 9. And I'm going to run it. And now I'm going to run everything below. So now I'm just going to run everything below after, so I'm recreating the network with now 9 by 9 filters. And let's see, so it's training. Okay, so there's the sample image of input. Because now these filters, so now these are 9x9 filters. So because these filters are bigger, they're looking at bigger patches of the input. And because they're looking at bigger patches of the input, they're producing filters that are more like a recognizable feature. So this first row, third column seems to be looking for a bright spot above a dark spot. Okay, so it's looking like you could think of this as an edge or some combination of two regions. Some of these filters, it's really not obvious what they're looking for. They don't have any recognizable, they look like noise. And again, some of these other filters might be looking for corners in different arrangements. Okay, and again, we look at the transformations that get produced. They're probably a little bit more, well, it's hard to say if it's more, if it's a bigger transformation than what we saw before. It's definitely a different kind of transformations. Okay. So that's my quick tutorial of digit recognition using Keras. I'm going to go back to the slides and wrap up. Okay, so other things you can do with these convolution networks, you can do feature extraction. You can run a network. So nowadays, by the way, a lot of tools have networks that are pre-trained that are available for you to use. So you could take, if you have a bunch of images, for example, you could run a Keras network. You could say load one of these pre-trained networks that have already been trained on images. And now I'm going to take one of these, let's say the last layer, and feed it into a different classifier. So this is for transfer learning, kind of thing you can do with these networks. That's kind of makes them very useful. The networks are starting to improve in terms of what they do. So people have decided or realized that besides recognizing objects, it would be nice to, let's say, segment objects. This could be very useful for a lot of biomedical imaging. There's a lot of tools out there. Again, TensorFlow, PyTorch are two examples of the lower level libraries to help you build these networks and help make it fast processing to run on GPUs or CPUs. I find that if you're running a network, even if it's a big network and it's already been pre-trained, you can run pretty fast on just a regular Comet node. If you're going to do some training, and if it's a fair-sized network, you're probably going to want to use a GPU. But again, it depends how many images that you have and how big the images are. But that's what I've been finding generally. Keras is a tool that, again, it's built on top of TensorFlow. It runs fairly well, and I think it might be the best one for learning. Other people, I've read in blogs, other people say it seems to be best for learning. I've started to use Caffe 2. Caffe 2, so Caffe was originally a library that came out of Berkeley. It had some good models with it, but Caffe 2, Facebook kind of took over Caffe 2, produced Caffe 2. It runs on PyTorch. It's a little bit harder to learn. The documentation's not as good. I have an example of that. I have used something called YOLO and Darknet. It's a C++ library. It's just if you like using, if you just like having all the code with you, that could be nice. MATLAB actually has convolution networks, and they have some pre-trained networks available. With MATLAB, you're only going to use a GPU because they don't run on the CPUs. And I find that MATLAB has, for standard stuff, it's okay. It doesn't have all the functionality you might want, but it's getting there. And again, there's a lot of these pre-trained networks available. Google actually has a API tool that's available through something called Google Vision. It'll give you, so if you give it pictures, you can run this, by the way, you can run this on Comet through Python and just run directly into the API, so you can process a lot of images this way. I ran some tests with these. I was looking at some old images with someone as part of an Exceed project. On the left, you can see it does a pretty good job. Here's an old picture of a band, and it recognizes that there's people, that there's musicians, It's, black and it describes the photograph. On the right side, it thinks that one of the highest categories it predicts is military or recreation. And it's just an old picture of someone, farming. So we can recognize as humans, we can do pretty well because we can see that there's a big stack of hay there. But it does recognize, now notice that Google did recognize that there was grass. Okay, so that's the Google example. As I said, Facebook has this Detectron network available in Cafe 2. Facebook is interested in persons. And here's an example where, so in this network, they have an option where you can just get people detection or object detection in general. So object detection is really something that's been people have been working on, not just people, not just detecting people, but detecting objects in general. And in this case, when you're detecting an object, you're typically producing a bounding box around the object. So here's object detection of persons. And this Detectron will also segment persons. So here, they're segmenting the different people with different shades. Notice that they don't recognize the Christ figure in this old painting. So it does pretty good. And these things, again, these things are trained with typically, modern images that you get off the net. They're not really trained for old paintings. So it doesn't recognize the Christ figure, and in some sense you couldn't blame it because that's a pretty, it's drawn, the painting itself is like, we recognize it as humans, but it's not a regular looking human. But we also get with the Detectron is the option of having key points. Okay, 1235. 35. Okay. So the option so the direction that people are moving in with this object recognition is you'd like to be able to recognize parts of objects or interesting points or key points. So here for people, this Detectron will tell you where the knee is, the wrist, elbow, shoulder, and some of these axes, long limbs. Okay. So just let me wrap up. Here's some references, some tutorials I used, and that's it. And if you have any questions, I'm happy to